Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to introduce Mark Stephenson from MIT. Mark has been working with Saman Amarasinghe. Mark just defended his thesis on, I think, was it Saturday? Friday. And so Mark has been working on the problem of how you construct compiler heuristics. He's been looking at using machine learning to automatically construct compiler heuristics. I think this is pretty interesting work since it's a time-consuming thing to construct compiler heuristics and difficult. So with that, I'll turn it over to Mark.
Thank you, David. Today I'm going to talk about how we can automatically create powerful compiler heuristics using machine learning techniques. So the motivation for my work is really that compilers are too complex for humans to really understand. In my research, I've looked at 3 different compiler infrastructures. And they range in size from 300,000 lines of Java code to 3.5 million lines of C and C++ code. And I realize that lines of code isn't the best metric for complexity in the world, but this does give you some idea that these are pretty complicated tools and that they're performing a lot of analyses and sophisticated transformations. And I also want to point out that the compiler really is critical for achieving good performance on modern machines. A study at the University of Virginia shows that compiler technology accounts for anywhere from 2.5 times to 17.3 times performance improvement on a common set of applications on modern machines. So the portion of the compiler that I'm most interested in is the code optimizer. And the code optimizer is really composed of a lot of these sequentially applied optimizations. And each one of these optimizations kind of performs its work very locally. And the optimizations aren't well coordinated with each other at all. So for instance, there are some cases where the optimizations are actually at odds with each other. The instruction scheduler prefers to move instructions far apart, and that is at odds with the register allocation pass. So because of these complicated interactions between optimizations, the compiler optimizations are rarely optimal. But probably the biggest reason that compiler optimizations are hard to perform well is that compiler problems are NP-complete. And this means that the compiler really can't afford to optimally solve the problem. And instead, the compiler has to rely on heuristics that perform fairly well in practice, but one major caveat is that they require a lot of tweaking in order to achieve suitable performance. And like David said, people will spend a lot of time tweaking these heuristics because they are so important for attaining good performance. So my approach is we can use machine learning techniques to automatically create powerful compiler heuristics. And the benefits of doing this are threefold. First, we can really increase the compiler's performance. The machine-learned heuristics that my techniques have come up with actually outperform the human-constructed heuristics by large factors in some cases. We also, once the infrastructure is in place, we can significantly reduce the amount of effort that's required to construct the heuristics. And then finally, this is a very important point, we can easily retarget new architectures with these techniques. So the Pentium 4, what are there? Currently 16 versions of the Pentium 4 out there with subtle variations between the architectural components. So this is a very important point. And I want to emphasize the point here that I'm not making any claims about reducing compiler complexity. My techniques focus on dealing with compiler complexity and achieving good performance in the face of it. So let me provide an outline for the rest of my talk. I'm first going to talk about my approach, which I call meta-optimization. And then I will show 2 different machine learning approaches that I've used. One is called policy search, and we can use policy search to find effective priority functions. And then we can also apply another approach called supervised learning. And collecting enough data to adequately train a compiler heuristic is kind of a difficult problem. So the focus of my most recent research is to mitigate this data requirement need. Yes? Right. Okay, I'll get into all that, but I'm really looking to optimize, to actually create compiler heuristics that you embed in the compiler itself. So I'm like, so yeah, I mean, I'll definitely get into this, but for instance, loop unrolling, we'll look at some characteristics of the code and train a machine learning heuristic to identify situations in which unrolling was beneficial. Exactly. All these things that I could choose parameter values. Yeah. So maybe later in the talk you can stop me if I haven't answered it. And then finally I'll conclude. So my approach really benefits from the fact that many compiler optimizations are naturally split up into two separate components. One component ensures that the compiler will generate correct code. And essentially, this component finds a set of legal options that the compiler can apply. And then the second component, which I call the policy, deals exclusively with performance. So the policy will choose from the set of legal options that the previous stage identified. And my approach then is to use machine learning to automatically create these policies. And one important characteristic of this approach is that any policy that the machine learning algorithm comes up with should generate correct code. So this is very important from the user's perspective, because the user expects that the compiler is going to generate correct code. But that said, my techniques did find some situations, they did come up with some policies that generated incorrect code. So you can also use these techniques to debug a compiler. So let me explain one optimization that's naturally split up into these two components. It's the basic list scheduling heuristic. And any priority-based heuristic is split up into these two components. So the graph on the left there shows a set of instructions. And the edges between the instructions correspond to dependencies that have to be fulfilled. So instruction E can't be scheduled until D has been scheduled. So the correctness component here for this algorithm will go through and identify the set of instructions that can legally be scheduled in the next issue slot. And then the policy will go through and apply a priority function to assign a priority value to each of these instructions. So here the priority value is assigned just based on the dependence, or the height in the dependence graph, or the depth. And then the algorithm proceeds by kind of blindly choosing the instruction that has the highest priority value, and it schedules that in the next slot. So the effectiveness of this optimization completely boils down to this policy, or how well it generates code. So because of that, I call these priority functions a heuristics Achilles heel, at least for the priority-based heuristics. They're really small, but they completely dictate the effectiveness of the optimization. And another reason why this is a great place to apply machine learning techniques is that they're prevalent in compilers. If you grep through the source code for a compiler looking for a priority function or cost function, you're likely going to get a lot of hits. And then, again, let me emphasize that any priority function is legal, or it should be. So the user expects the compiler to generate correct code. Let me talk about another priority-based heuristic that's really important for modern architectures. So first I'll motivate the problem, and then I'll describe a state-of-the-art man-made heuristic and priority function for solving that problem. And then I'll show how we can use policy search to find better priority functions than those that the humans generated. And then finally, I'll provide results. And for this segment of the talk, the compiler that I use is the impact compiler. So hyperblock formation is really motivated by the expense of branching on modern architecture. So architectures are really aggressive, and they'll try to execute code before they even know whether or not the code should be executed. So here the processor will make a prediction about which direction the branch is going to take, and it'll execute instructions along that predicted path, and it won't find out until really late in the game that it's made a misprediction. And then at this point, the processor has to nullify all of these in-flight instructions and begin executing instructions, again, from the beginning, this time executing instructions along the correct path of control flow. So on the Pentium 4, that architecture has to nullify up to 120 instructions when it mispredicts. So this is potentially very expensive. So an alternative to standard control flow is called predicated execution. And with predicated execution is a very compiler-driven optimization. So the compiler will, I'm not going to talk about it in details, but the compiler will form these hyperblocks. So essentially it'll merge the instructions together from the different paths of control flow, the then part and the else part, into a single predicated hyperblock. And this allows the instruction scheduler then to rearrange instructions so that instructions from the then part and the else part can execute simultaneously. So here the processor can execute instructions from both paths of control flow simultaneously, and it will just discard the results of instructions that weren't supposed to be executed. So there are a lot of trade-offs to consider when we decide whether or not to predicate control flow. In some situations, forming hyperblocks is definitely more efficient than executing in a standard control flow fashion. But in other cases, it can really degrade the performance. And there are a lot of factors that go into making this decision. So for instance, if the branches are highly predictable, you probably don't want to form a hyperblock because the processor would likely predict the right path of control flow, and you could use all of the machine's resources to execute that path. So in short, this is a really hard problem to model, and humans have a difficult time with it. Let me show you a human-constructed heuristic for it. This comes right from the Impact compiler. First, the algorithm identifies the regions of control flow that can legally be predicated, and then it will enumerate the paths of control flow in that region. So the first two stages here correspond to the correctness enforcing component. But from this point, the algorithm's really simple. It just looks at each one of these paths that the previous stage identified, and it will prioritize them based on 4 characteristics of the path. And this is the priority function that we want to optimize. This completely dictates the effectiveness of the optimization. Because from here, the algorithm will just kind of blindly merge these paths together in order, in priority order, merge them together into a single predicated hyperblock. And it will stop merging when the machine is run out of resources. So let's look at the priority function for that optimization. Again, a priority function is a function that takes as input some number of characteristics that describes a path in this case, and it returns a single value, which is that path's priority. And again, this is the critical part of that heuristic. The performance hinges on this priority function. And it's a pretty straightforward priority function. It favors frequently executed paths. It penalizes paths that have instructions that might lead to exceptional conditions. It favors paths that have a lot of instruction-level parallelism. And it favors short paths. So, I mean, it's intuitive and it makes sense, but one interesting thing are these magic numbers here. So why did they use 2.1, for instance, instead of 2? Well, 2.1 probably led to a little bit better performance on the benchmarks that they were testing it on. So people do tune these priority functions. So the priority function that I showed you on that last slide used 4 characteristics to assign priority values. But there might be a lot of other characteristics that are just as important. And so my approach then is to extract any features that I think might be important for assigning priority values, and I'll let a machine learning algorithm find the priority function for us and do some sort of feature selection. So to that end, I extract things like the number of operations in the path, the predictability of the path, the number of branches. All told, I extract about 20 features, or over 20 features. And then I feed them to a machine learning algorithm. And the machine learning approach I use is called policy search. And in policy search, an agent tries to learn how to adapt to its environment over time. And I'll explain this a little bit better in a second. But there are many ways to represent a policy in policy search. For these experiments, I use genetic programming. So in genetic programming, a policy is represented as a parse tree. So this is a form that's very familiar to compiler writers. And this is actually one of the major benefits for using genetic programming, is that the compiler writer can actually look at the policies that are being generated and glean some interesting insights. So I don't want to take the analogy too far, but genetic programming is an approach that's somewhat analogous to natural selection. It maintains a population of these policies, or in this case, again, the policy is a priority function. So it maintains a population of these priority functions. And the priority functions that perform best in the given environment are favored for reproduction and mutation. So let me explain that a little bit more clearly. The priority functions that generate the most effective and efficient code are deemed to be fittest. And these priority functions then are favored. So the algorithm will select the most fit individuals and use this subset of fit individuals to breed a new population that will work in the next iteration of the algorithm. Let me explain it a little bit more concretely here. So the algorithm first starts with a completely random set of priority functions. So these are completely randomly generated. And you can seed the initial population with the compiler writer's best guess, but I've noticed that this has very little impact, almost no impact. The human's best guess is quickly weeded out of the population. So in the next stage, we will take the compiler, and we'll have a little stub here. So again, we're looking at the hyperblock formation problem. We have a little stub where we'll take one of these priority functions, plug it into the compiler, and use it to compile a set of benchmarks. And we can run these applications then to get an idea of the fitness level of that priority function. And we do this for all the priority functions in the population. And then again, this genetic programming policy search will favor the policies that perform the best. So it's a non-deterministic approach, but it does favor the priority functions that perform best. And then using these priority functions, we can create a next generation, a new population with these reproduction operators, and we can also mutate some of these priority functions to innovate possibly stagnant populations. So I kind of alluded to this, but there are a lot of different ways we can train the priority function. So most people, when they think of a compiler, they think of a tool that performs well on a wide variety of inputs. So performs well on an MP3 player or a molecular dynamics simulator. And furthermore, the users expect that the MP3 player that their compiler compiles will perform well on a wide variety of input programs. But if you talk to an embedded systems person, they might have a different view of the world. They would want a compiler that performs awesomely on the one application that they're developing. They don't care if it generalizes to other applications. So we can train a priority function that's catered exactly to a specific application. And let's further constrain it to find out kind of the best we could do by creating a priority function that works great on a single application that runs a single input data set. So before I show you results for that, let me explain my experimental setup here. Again, I'm using the Trimaran VLIW simulator, which is a popular simulator that is somewhat similar to the Itanium processor. And I'm using the impact compiler, and I replaced the human-constructed priority function with this genetic programming parser so that the policy search algorithm can quickly swap in and test new priority functions. So let me show you the results. Before I actually flash up the bars there, let me explain the axes. On the x-axis, I have the benchmarks, and the y-axis is the speed up over the human-constructed priority function for hyperblock selection. So again, we can use policy search to come up with a priority function that's catered exactly to this 129 compressed application running this single input data set. And doing so, we get a 229% improvement, which shows you that there is a lot of flexibility in these priority functions, and it's important that we tune them well. And we can do the same thing for G721 in code. We'll come up with a different priority function this time that's catered exactly to that application. And if we do the same thing for all the applications on the x-axis here, we get a 43% overall improvement, which is really good considering this was completely automated. But it's kind of unreasonable to assume that the application is only going to ever run a single input data set. So if we apply an alternate data set to each of these applications, the performance is diminished a little bit, but we still get a 21% overall improvement. So again, there's a lot of flexibility in these priority functions. So let's return to the, yeah, Ben.
Is there any insight about why compressed did so poorly?
I actually haven't gone through and gathered, I really don't know why, but it is clearly exercising different paths of control flow.
So is it a problem of overtraining? Basically, give it too much. You make it really good for that one input, but it's not going to be quite as good for the other.
That could be one thing. For this problem, I did train it on the alternate data set, and I didn't do much better than this. So. Yeah, that is an interesting case. Again, it's just exercising a different path of control flow.
Does that do anything with the original compilation, or that's
No, it was not trained on the orange bar at all. I just took I trained it on the blue bar, got a priority function, and applied that to the orange bar. So there was no training involved. We just learned the policy and used that policy to compile. I guess we just, all I did is I took the application that the compiler spit out, and I applied a different input data set to it.
So in your training set, was it just one input data set per program, or was there multiple sets?
There were I think there might have been about 5, and I just chose 2 that were roughly similar to each other in terms of workload. So I didn't want to get a case where I was training it on a really small input and applying it to a larger input. So let me talk about the original view of a compiler again. So here we expect it to perform well on a wide variety of input programs. So we can train it to do that, to do well on a whole set of applications. And that's what this graph shows. So here on the last slide we had n different priority functions, each catered to a specific application. And here we have one priority function that we apply to all of these applications. So if we use the same input data set, the blue bar, if we use the same input data set that we use to train the priority function, we get a 34% overall improvement. And if we apply an alternate data set, we get a 21% improvement. So it's clear that since now we have one priority function that does well on a wide variety of input programs, that the priority function might have latched onto something interesting. To see if this is really a general priority function, though, we can apply it to a validation set. So these applications were not in the training set. These are just a completely different subset of applications. And so overall, for these applications, the approach gets an 8% improvement. And there are a few cases where we marginally slow down performance. But for the most part, we do pretty well. So the priority function is general purpose. And let's look at the priority function that the approach came up with. As with other genetic programming solutions, there's a lot of bloat that doesn't really affect the solution. But this does some interesting things. It favors paths that don't have pointer dereferences. It favors paths that have a lot of instruction level parallelism again. And if a path makes a call to a subroutine that might have side effects, then it'll penalize it. So again, it's doing some similar things to the human constructed priority function. But the relative importance of the certain characteristics of the paths are different. And I guess about 8% better for this one.
So you use Trimline?
Yeah.
Could you change the characteristics of the hardware, the simulated hardware, and see if you could zero in on the new hardware?
See if I can.
How that would compare with
I didn't do that, but I could do that fairly quickly.
Yeah, I was going to say that would validate your hypothesis.
You could be
Quickly track the changes in the hardware.
right. Yeah, that's a good question. Let me mention the running time of this approach. To train these application-specific priority functions, it took about 1 day using 15 processors. So it's a fairly expensive approach. And to come up with the general purpose priority functions, it took us about 1 week. And here we used a couple of techniques from the genetic programming community to reduce this running time to 1 week. But there are a couple things that I need to emphasize here. First of all, we're training policies, so we can always use a best so far solution, and we'll still generate correct code. And so we don't need to necessarily train for a week. If you're strapped for time, you can train for less time than that. And the other very important point, that this is a one-time process. The user doesn't see any increase in compilation time. This is it's performed by the compiler vendor at the factory, and the compiler vendor ships the compiler with this machine-learned priority function. So, okay, let me move on now. Sorry.
There's another question about the amount of training. So, is there any appreciable, I mean, you ran for a day, is there any appreciable value in running it for longer, or if you ran for an hour, would it be 80% of what you got?
It depends on the priority function, or the problem, sorry. For register allocation, it was a much more challenging problem to solve than than hyperblock formation. So hyperblock formation, the algorithm very quickly zeroed in on a solution that was close to what it would get if we let it run for much longer. For register allocation, though, the solution converged much more slowly. So it does depend on the problem.
Do you have a sense as you're running the process of training that it's converged, basically? I mean, is it one of these where you just have an automatic shut-off that, you got very little in the last hour?
You probably could do an approach something like that, but I wouldn't trust it that much, because a lot of times what you see are these quantum leaps where you just kind of plateaued for a while, and then all of a sudden the approach found something very interesting that really increased its performance. So you can apply this policy search to pretty much any compiler policy, but there are certain situations in which supervised learning approach is probably more efficient and more effective. So I'm kind of a baseball fanatic, so let me give you a baseball analogy here. In the game of baseball, a manager doesn't have a complete model for every single player who's out on the field. And so the manager will make decisions based on simple statistics and past performance data. And in the same way, the compiler doesn't have a complete model for every compiler pass it applies. It doesn't have a complete model for the target architecture. But can we use statistics and machine learning and empirical performance data to recognize the cases in which a particular optimization was beneficial? And we can, and let me show you an optimization that I've experimented with here. It's loop unrolling, which probably all of you are familiar with. It's a really simple optimization that replicates the loop body. It also adjusts the increment of the induction variable. And loop unrolling can benefit a lot of downstream optimizations. So for instance, now we might be able to partially vectorize the instructions in the loop body after we unroll it. But of course, it's a much harder problem than just trying to determine whether or not we need to unroll the loop. We also need to determine how many times we should unroll the loop. So we could unroll it 4 times or 8 times. And really determining the unroll factor is kind of a balancing act. It's a very difficult problem there. A lot of trade-offs. If we just unroll all the loops by a large amount, we're definitely going to decrease performance because we'll thrash the instruction cache, and we'll also hinder the performance of the register allocator since we're really creating more and longer live ranges. And who knows what other interactions there are with the other passes. So from my perspective, one interesting thing about this, and it sets me apart from some of the related work, is that it requires categorization into multiple classes. So what I mean by that is we need to determine the unroll factor and not just whether or not we need to unroll the loop. But we can use an approach called supervised learning to solve this problem. And the goal of supervised learning is to create a function that takes as input a vector of characteristics that describes an object and returns a prediction about what should be done with that object or what category the object's in. So for the loop unrolling problem, we want a function that takes as input a vector of characteristics that abstractly describes a loop. So these are things like the number of operations in the loop, what kind of a loop it is, how many forward branches there are, that kind of thing. And then we want this function to return a prediction about how many times we should unroll that loop. And supervised learning works on a training set of examples. So here this light gray circle represents the set of all possible loops. And remember that loops in this space are characterized by a vector of characteristics. And we can create a training set of examples, which is represented by this dark gray circle. And here, each one of the white circles in the training set corresponds to an actual loop. And a supervisor will go through for each one of these loops and find the empirical best unroll factor for that loop. So hence the name supervised learning. So the supervisor will go in, take a loop, and test out the loop at all the different unroll factors up to some limit, and then choose the unroll factor that led to the best performance. And then that's that loop's label. And once this training set is in place, we can run supervised learning to automatically create this function for us. And some supervised learning the supervised learning algorithm will come up with a function that tries to minimize the error on this training set of examples. And some supervised learning approaches actually also try to simultaneously minimize the complexity of the function to help with generalization. But once we have this function in place, we can look at a new loop that was outside the training set of examples, apply the function, and we'll get a prediction about the unroll factor. Yeah?
You simplify the problem here in that you can choose what the unroll of the individual loop, but those will interact with each other in actual program.
You're right.
So how do you deal with complexities like that?
Well, you'll see in the results that the training data that we did collect is somewhat noisy. So there are some cases where the human constructed heuristic outperforms the best we could do according to our training data. So this simplification really did help us collect a lot of data that we could use to create effective heuristics.
But this is just a structural problem.
It is a problem. I mean, there are potential ways that we can solve this problem, but this is a much more efficient. Instrumenting the loops in bulk is much more efficient for extracting the data.
That's what the is.
Sorry? Okay. So that's a good question. To collect this training data, there are essentially two critical pieces of information that we need to extract for each loop. We need to extract a vector of characteristics that describes the loop and the label that is the best unroll factor for that loop. So let me first describe how we extract the features. Here, for this set of experiments in this segment of the talk, I use the Open Research compiler, and I target the Itanium 2 architecture. And most of the features for loop unrolling were readily available in the loop unrolling path. It was extremely simple to extract this vector of characteristics. And again, these are things like the number of operations in the loop and such. And so all told, I extracted about 40 characteristics to describe the loop. And then I don't have time to talk about it here, but I used feature selection techniques to automatically identify a much smaller subset of these features that were the most informative for the problem. So I reduced it from 40 features down to 9 highly informative features. And then to extract the labels for each loop, I added an instrumentation path that essentially inserts assembly instructions before each loop that start a timer and assembly instructions after the loop that will stop the timer and accumulate the elapsed running time into some memory location. And then at all exit points, I insert a call to a library that will dump out this raw timing information. So then with this infrastructure in place, it's really easy to find the optimal unroll factor for the loop. We just compile and run each loop at all unroll factors up to some limit and choose the unroll factor that led to the best performance. So once we have the training data, we can induce these heuristics and actually plug them into the compiler to see how well they perform. And that's what this graph shows. The x-axis shows the benchmarks that we use. These come from the Spec 2000 benchmark set. And the y-axis shows the speed up over the human-constructed unrolling heuristic. And the yellow bar for each one of these benchmarks corresponds to kind of the best we can hope to achieve with the training data that we have. So if we make perfect predictions according to our training data, these are the results that we would get. And then we found that 2 different machine learning algorithms worked really well for this problem. First is a simple nearest neighbors classifier, and the other is a support vector machine with a radial basis kernel function. And so you might notice that the benchmarks on the left perform very well. These come from the Spec FP application set. So these applications are highly amenable to loop optimization. And the Oracle, the best we can hope to achieve, gets a 12% performance improvement for these applications. And the support vector machine gets a 9% improvement. So it's doing pretty well. And for the applications on the right, they come from the SpecInt application set. And these prove to be very difficult to optimize with loop unrolling. The best we could hope to achieve gets a 1% performance improvement. And the classifier, the support vector machine, and the nearest neighbors approach actually get marginal slowdown, about a 0.5% slowdown piece. So, I mean, I guess I could have just left these out of the slide and trained specifically on the floating point application. But sorry, yeah?
On 254.gap, how can the Oracle have a database?
So that's what I'm talking about. Yeah, we instrument all the data in bulk. So we'll unroll when we see how well unroll factor 8 applies. We'll unroll all the loops in the application by 8. So that's the noise that you were talking about, and so that's why we do have some cases like this where the Oracle's outperformed. So yeah, when we make perfect predictions, I say we make perfect predictions according to the training data that we collected.
So what was the maximal from? Just saw it said 9%.
12% for the Oracle, the maximal on these benchmarks.
Oh, okay, that's the new one.
The geometry. And then we got a 9% with our classifier. So let me also point out that the way I collected this data. So when I collect the results for 179 art, I will hold out all training examples from that benchmark. So I'll train on all of the other applications, and then I'll induce a heuristic with that data and test it on art. So in this way, we see how well we generalize to applications that weren't in the training set. Okay, so I hope I've convinced you that meta-optimization can really produce powerful heuristics. In practice, one problem we have is collecting enough machine learning data to adequately train these heuristics. So the focus of my most recent research, and it's still very much a work in progress, is mitigating the stringent data requirements of machine learning. So again, we know that in order to create powerful heuristics, we have to really train on a lot of data. And this data has to be drawn from a very diverse set of applications. And hopefully these are applications that the users actually care about, because I'm essentially training the compiler to perform well on the applications that I want it to perform well on. But there's no guarantee that users are really interested in them. And we've also seen that applications that are in the training set perform much better than applications that are just in some validation set. So what if, instead of training at the factory, we can train right on the user's desktop and train with applications that the user really cares about? And so in this way, we could adapt to the usage patterns of a user or a whole community of users. And in order for people to actually use this, the training process would have to be completely oblivious to the training process. So let me describe collaborative compilation. These are the goals of this collaborative compilation system which we've developed. So let me describe the traditional approach. The collaborative approach really works best within a virtual machine setting. So let me describe the major differences. In the traditional approach, the software vendor will take an application, compile it, and ship this precompiled executable to the user. And the user can directly run it from there. So here we have a compile once, used millions of times type of an approach. Well, Java and Microsoft.NET have really popularized a different approach where we ship bytecodes now. The software vendor ships bytecodes, and a virtual machine will interpret this application. But these aren't simple interpreters. They actually have fairly hardcore compilers embedded in them. And so now we have an approach where every single time the user runs an application, the compiler is invoked. So if we can somehow harness this to collect machine learning data, we'll have no shortage of machine learning data. Let me recap the approach that we use to collect the loop unrolling data. We take an application, we'll compile it. The compiler will extract some features for loops or methods or whatever it is we're trying to measure, and it will instrument an application. When we run this application, we'll collect runtime information, raw runtime information that we can use to assemble a machine learning database. When we have this database in place, we can run it through a machine learning algorithm and insert it into the compiler, the induced heuristic. So let's just look at the data requirements. Again, we instrument all of the loops in bulk here if we're measuring loops. So just for efficiency reasons. But this can have substantial compile time and runtime overheads, and it would definitely not be transparent to the user. So instead of instrumenting every single loop, what if we just instrumented a very small fraction of the loops in a user's application? And instead of running it on a single client at the factory, what if we could distribute this data collection over lots of clients on a network? And so before, we had a single client that was extracting a massive amount of machine learning data. But now we have lots of these different clients, each extracting a very small amount of machine learning data. And these clients will send their data to a centralized repository where we can aggregate very quickly a substantial amount of machine learning data. And these clients aren't going to want to suffer the consequences of the slowdowns from instrumentation. So we have to give them something to compensate them. So here we can give them the latest and greatest machine learned heuristic, which will improve future invocations of their just-in-time compiler. So I mentioned that for the traditional approach, we would just extract the data in bulk. But here we can do a couple of things to really lower the overheads of instrumentation, so to the point where the user doesn't even realize that their code is being instrumented. Again, every time the just-in-time compiler, every time the user runs an application, the compiler is invoked. So instead of instrumenting every single method that the compiler compiles, let's just instrument a very small subset of these methods. So let's say that this method was one of the ones that was chosen for instrumentation. If we were testing to see whether or not loop unrolling performed well if we were trying to find out the cases in which loop unrolling performed well, we could create two new versions, each of which were optimized differently. So in one version, we would keep the loop rolled, and in the other version, we would unroll the loop. And then we could insert instrumentation at the top of the original method that would randomly sample between these two newly created methods. And we'd also wrap timers around the calls so that we'd keep enough information to compute the mean and the standard deviation of the runtimes for different invocations of these methods. And so then with this information, we can just apply a t-test, essentially, to determine if loop unrolling is beneficial for this loop, or for this method. And one thing I want to point out here is that most of the time the original portion of code is executed. We won't sample very frequently. So this combined with the fact that we instrument very few methods to begin with keeps the overhead of collaborative compilation to almost nothing. And this naive approach really won't work because of noise in machines. So here what I'm plotting are the samples from two different methods over time. So yeah. Right. Right. So I can kind of interpolate between? Yeah, that might be a... Yeah, that might be an interesting approach. But again, all of my techniques, they really don't have compile time. Well, this one has a little bit of compile time overhead, but my other techniques do not affect the compile time at all. It's not a stringent requirement, but I think most users aren't willing to put up with a 2-day training period.
Right, but you need to make compile time a little higher, but
Sure.
Yeah,
Exactly. Returning to this, the y-axis shows the runtime for each of the invocations on the x-axis. And one thing about this slide that might be surprising is that version 1 and version 2, these two different methods are actually identical to each other. The only difference is where they reside in memory between them. So these alignment effects can have significant performance, can lead to significant performance degradations or improvements. So things like it'll affect the instruction cache, the trace cache, the branch predictor. So even though version 1 and version 2 are identical, version 2 is about 7% faster. So if we can't identify these situations, we won't be able to collect very good machine learning data. So one approach is just to create redundant methods. And so here we'll create two versions of the method where the loops are left rolled and two versions where the loops are unrolled. And again, we'll compute the mean for both of these. And if we see a substantial difference between the means for identical methods, then we know that there's a problem. And again, I need to mention that the alignment issue doesn't happen super frequently, but it happens frequently enough that we should be concerned about it. So identifying these situations is important. So let me show you an experiment that we performed to see how well we can filter out the noise. Here we'll use the same infrastructure to create two methods that are identical to each other. And then we'll compare the runtime ratios. So because they're identical to each other, we expect the runtime ratios to be 1. So if we plot a histogram of the runtime ratios that we extract using that approach, and this is over thousands of methods in a Java benchmark set, we see that the histogram is centered around 1, which is good, but there's a lot of noise in the system. So I set up this kind of arbitrary 3% noise tolerance, and only 64% of the samples lie within that tolerance. So if we apply this redundant method filtering, we can really squish this histogram together so that now 86% of the samples lie within this 3% tolerance. So we think that we can use this kind of machine learning data to induce heuristics. And we have a very preliminary result where we look at method inlining. And here, all we do to train the benchmark, to train the heuristic in this case, is run the application. So here we repeatedly run bloat on this blue input data set. If we run it for about 8 hours, during the course of that time, we collect around 600 samples that we can use to improve future invocations of the just-in-time compiler. So just by running bloat for about 8 hours, we get a 13% improvement. The user didn't have to do anything but run the application. And, yeah. Sorry. The y-axis is the speed up over the JIKES, research virtual machines, human constructed method inlining. On everything's the same except the running on the same machine. Yeah, again, this is a preliminary result. And if we do the same thing for all the benchmarks on the x-axis, overall we get a 5% performance improvement. And if we apply, again, using the same approach we did before, an alternate data set, we get a 4% improvement. So, I mean, it's an encouraging result. There's still a lot of work to be done, though. Let me talk about some related work before I conclude. Elliott Moss used an elegant reinforcement learning approach to induce instruction scheduling heuristics. But it's not clear whether or not the approach is appropriate because the human-constructed heuristics outperform the machine-learned heuristic. A lot of people have looked at using supervised learning to induce heuristics for binary problems. And I showed in this talk that we can use supervised learning to solve the harder multi-class problems. Researchers like Keith Cooper have looked at using genetic algorithms to solve phase ordering problems. But this approach really, it's very effective. They find great phase orderings. But the compile time overhead is really severe. And I don't think users would be willing to put up with that. And most closely related to the collaborative compilation approach is work by Diniz and more recently by Lau, where they use this dynamic feedback approach to improve the steady state runtime of an application. And the major difference here is that we use this approach to extract machine learning data, which can improve future invocations. But the infrastructures are similar. So let me just conclude by stating my contributions. I used machine learning techniques. I introduced an approach to create powerful priority functions automatically. And this is a very important place to look because priority functions are ubiquitous pretty much in compilers. So we need to really learn how to deal with them. And also I showed that we can use supervised learning to induce compiler heuristics for multi-class problems, such as loop unrolling. And there are a whole lot of other compiler problems that could benefit from this technique. And I didn't have time to talk about it here, but I show that we can use feature selection techniques to automatically identify the most informative characteristics for solving a particular compiler optimization problem. And this could be a very valuable tool for compiler writers to instruct them about what is the most important characteristic. And finally, it's still a work in progress, but we introduced this collaborative compilation approach, which we think might have a lot of impact down the road. So that's it. I'm happy to take any questions from you.
So one thing I didn't quite understand is what your loop unrolling algorithm actually, or your unrolling heuristic actually was at the end of the day. Was it just, you talked about, for example, unrolling with a fixed number of points. I mean, clearly, depending on what kind of loop you're looking at, that may or may not be a worthwhile heuristic.
A fixed number of times?
Like, say, just what was your heuristic? What did it come up with?
So that is one of the potential downsides to the approach is, in this case, for genetic programming is great because we could look at the heuristic. It was human readable. But for things like support vector machine and nearest neighbors, it's really difficult to glean insights from that. They're written in the paper, but the most informative one was the number of floating point operations in the loop. So, yeah.
And was it the higher or lower, or is it the fraction of floating point operations, or was it?
It was the fraction. Yeah, I had to normalize all of the features. The machine learning algorithms really work better that way. Yeah, I guess it requires a separate step though. Ben?
So, do you find that the number of features you do have any real impact if you give it sort of everything you think
No, that worked horribly. Yeah.
of?
Yeah.
So you have to carefully craft which ones.
I don't think you don't have to carefully craft it, but the feature selection techniques, you can really just say, give me the 10 best features for solving this problem, and then use those 10 best features, and the induced heuristics work out much better that way.
So why did the large number of features, why didn't that work out?
Because you can really overfit. If you have a lot of features, you can overfit the training data set very well. These machine learning approaches.
So if we had more input data, though, that might change.
Yeah, it could change.
I mean,
Definitely.
because, how people run programs in practice is quite different than just a small training sets. One lesson I'm taking away from this is that compiler writers generally don't have such training sets.
Exactly.
Input data.
Well said. Yeah, I mean, I scrapped together about 70 benchmarks and still seem to. I do regularize. I guess it depends on the approach, but for instance, for nearest neighbors, that's not going to help at all.
So in terms of your applying the technique to create priority functions, what other optimizations do you think would be useful? And a quick question would be, and where do you think that will break down?
So I've already applied it to register allocation. I didn't show it here. I've applied it to register allocation and data prefetching. And it worked fairly well for both of those problems. Especially register allocations is extremely well-studied optimization. So, I mean, we used the same exact approach. I spent maybe a day setting it up and, let it run for a week. And we got a 3% performance improvement. So, in terms of...
What kind of register allocator was it?
It was Hennessy Chow register allocator.
What machine was it running on?
It was the Itanium machine again. And I tried it out on 32 and 64. register machine.
Okay, so you got a 3% even machine.
Yeah, it did. So, and in certain cases, I mean, it got fairly large speed, up to 8%. So, I don't really have a great feel for where it's going to break down. There are a lot of optimizations where the policy is really intermingled with the correctness checking component. So in those cases, it's not easy to apply the machine learning technique. But I think for any heuristic or any optimization that's crafted so that you have these two separate components, the correctness checking component and the policy, I feel like these approaches will provide benefits.
What about the case where an optimization has sort of a cascading effect? So you could pick something like CSE, where CSE, doing this one CSE may have a cascading effect on your ability to do future CSE.
That's a great question. I think the loop unrolling problem is very much like that. And I mean, I think it's very possible to predict early on how how well a particular optimization will apply, given a fixed set of downstream optimization. So.
Did your loop unrolling, when you're talking about nested loops, is that the
I test the innermost loop of a nested loop. So I guess the next step will be to try to kind of co-learn different optimizations to come up with a nice symbiosis between a couple of different optimizations. So right now I've focused kind of on a single optimization at a time. So, yeah.
You said this helped you manage complexity of complexity. I mean, if you look at it as kind of computational, like you managed to have the complexity very locally, because you have the optimization of each of the priority functions for each optimization, and you have the interaction between optimizations. Maybe you want to have a different inlining strategy if you have a better CSE optimization problem.
Mm-hmm.
If you learn one set of optimization functions, like priority functions for one optimization, then you move to the next optimization. Maybe your priorities were wrong.
Yeah.
And then there's the big phase order problem, which is huge. So kind of solve 1 out of 3 problems.
I actually looked at the phase ordering problem. I was telling David this earlier, and it proved to be extremely challenging. So yeah, it was very difficult to predict when a particular phase ordering was applicable.
Yeah, I was going to say, what's the path to solving the whole?
I do think it would be very possible to co-evolve these priority functions. There's a lot of machine learning work that's focused on that. And so I think it's possible, given a fixed ordering, to come up with good policies that interact well with each other. Yeah, I haven't yet really investigated that, but that's one of the next steps.
So I'd like to, any other questions? Okay, so I'd like to thank our speaker.
Thank you.